So now we're on to gradient descent, which is a technique or method of optimization of continuous problems, where we work with real values and real valued functions. And now let's consider such an example. Let's consider that we are walking down the hill, and we want to get from that hill as fast as possible, because it's already darkening, and we want to get our camp, which is, so we have some hill and we have here camp, and we want to get to that camp as quick as possible, and it's quite dark already, and that's why we can't see whole hill, because it's dark. We can only we are working merely on our just intuition, and we're just stepping around to get knowledge about where the hill is declining or it's increasing. So we can't even see anything. We just can't step in different directions and say if this is a higher place or even it's deeper place. And we want to get as quick as possible because it's dark, and if we knew whole hill, whole distances and whole form of the hill, then it would be actually a pretty easy optimization problem. You could solve it, for example, with something like I don't know, like simulated annealing, because it's suitable for continuous problems, and you just define your path, and then you simulate annealing it. But we don't have this information. We have only information about our region, and that is the place where we're using partial derivatives again, and we will introduce, not very strictly, we'll introduce a mathematical operation which is called gradient. So first, let's consider the same example on a map. So here is our map, and this is, let's say this is a higher point, and this is lower point, and we want to get as quick as possible, so we can go in all different directions, but we're actually doing something right, and that's why we've chosen this direction, and it turned out to be the fastest one. So if we are considering this hill, then it can be again represented as some sort of functions which depends on your x and y coordinate, and that is the height of this hill. And we can step in x direction, we can step in y direction, or we can step in both, but we have only limited velocity, and that's why we can step only on limited distance. And if our hill looks like that, which means that its height doesn't depend on y direction, then it's obvious that we don't need to go in y direction, because we will just lose our speed there. And if our hill has more complex form, then we can consider that we will rather go in direction where slope of the hill is highest, which means slope of the hill depending on x and y coordinate, which introduces us back to partial derivatives. And actually it can be strictly proven in mathematical calculus that the fastest way to go down this hill is to step on x and y coordinates on amounts proportional to partial derivatives. So that's the first rule and it actually contains whole idea of gradient descent. And so I'll reintroduce it. So if we have right now we are a traveler and we have some coordinate x and y on this plane, then our z coordinate is just defined by how our hill goes, because we just can't go up and down because of hill and gravity. But we can do an iteration and change our values, x values, in that way. So that's some number. It's a Greek letter called eta. And we are going to change our coordinates a bit, and then we will get to some other point, x and y new. So this is how our travel should go, and we can do it iteratively, and eventually, hopefully, we'll get to our camp with the shortest time. And we can again recollect that, for example, if we have a big partial derivative, then it's better to go in this direction, because going in this direction will increase your speed of decreasing or descent. And if this derivative is equal to 0, then it's pointless to go in that direction. But actually, if we have something between these two cases, marginal cases, where all derivative is going on x or all derivative is equal to 0, we actually get that we should go in steps proportional to partial derivatives, which still means that it still works for our marginal cases, but it's defined in that way. And if we have more coordinates, and if we are talking about more complex models, which we will encounter in like 3 or 4 lessons, we will have to do the same operation, but for each variable. So if we have x1 and up to xn, then we just have to update our values like follows. And we are going to do it iteratively, which means that we won't just take a huge step in one direction, because we know only region of a hill, and we don't know how hill goes when we will get to this point, and we don't know the most beneficial way. So the most effective way is to take infinitely small steps. If we are approaching our number eta to infinitely small number, then actually gradient descent will be pretty good searcher for local minimums. But we just cannot do that, because computers don't like infinity numbers, because a loop need to stop somewhere, and that's why we have to balance between uncertainty of our hill behaving in other direction or in other way if we get to other point, which means that we cannot just increase our eta to be infinitely big and to take one step and get nowhere. And on the other hand, we cannot have our eta infinitely small, because in that case our computer will run forever. So this is a great problem of gradient descent, that we have to manually choose number eta for each particular problem to get successful fork of this. So let's now walk. Where are we? Like, that's how we're doing it. And let's consider an example of how we are going to optimize this simple function with two parameters. And so first step is to define this function, obviously. The second step, as you could see, we need a partial derivative of each variable, which means that if we have some analytical function, then we can calculate it manually. But sometimes our functions are too hard to derivatives of these functions are too big to compute, and it's computationally ineffective. It's quite a rare case where it's better to calculate in that way, not in the manual way. But sometimes some functions doesn't have derivative at all, and in that case you can take partial derivative by let's take a partial derivative with respect to x1, and then we can do it like an old way, where we took a small increase in value of x1, and then we are considering how our function behaves. And to xn, and then we are subtracting previous value of function and dividing by delta x. So that means that we are kind of taking derivative, just normal derivative again, but our other parameters from x2 to xn aren't changing, and this is a second approach to compute partial derivative. So if your function is too complex to calculate derivative manually, then you can go this way. And again, the problem is that you have to recompute, and you have to consider what delta x to have, because if your delta x is too small, then you can have a computational error. And if your delta x is too big, then you'll just have an error of finding this partial derivative, because this partial derivative won't be equal to this expression if delta x is too big. We mostly won't use this method because it's actually not effective sometimes, but sometimes it can be used. So we've computed, it's a pretty easy function, and again, x squared and y squared, if we are computing a partial derivative with respect to x, y squared is a constant, which means that we get 2x and 2y, and that's our partial derivative with respect to x and y. And again, we introduce another function which we'll just call PD, shortened for partial derivative, whose inputs are x and y again, and it returns two outputs. Our first one is a partial derivative with respect to x, and second one is with respect to y. And also let's build a color plot of this function, so you can see that this is the deepest point. It's 0, 0. It's pretty obvious because squares can be only bigger than 0, which means that in 0, 0 point we have the minimum, the global minimum, and it's actually the only one minimum, and that's why partly our gradient descent will work nicely in this example. And finally we are going to do gradient descent. So here we have our initial points from where our point travel starts each journey, and then we have some lists just to write down x coordinates to then plot them. And here you can see that we just find our partial derivatives. I've denoted them the x and the y, but not to be confused with actual. You don't need to be confused, it's just a denotion, and that's all gradient descent in 3 lines. You just find partial derivatives and then you apply this simple operation. You just subtract this dx and dy multiplied by number eta, and that number eta will play a huge role in how gradient descent works lately, as you can see. So now let's build. I've chosen, because eta is a very important parameter, I've chosen to plot several plots with different etas to show different behaviors that gradient descent can show. So first one is a very small eta, and because we have only 50 steps, we just don't get to global minimum, local minimum, and it shows that sometimes you choose eta too small, and in that case your computer can do computations very long. Then we've got a bit better, but it's not quite. And finally, for eta is equal 0.1, we get actually pretty nice results. So we can see that it's actually close to minimum or in the minimum. And then let's see what's going on if we're increasing eta again. It works again nicely, so we can actually consider choosing 0 or 5, and then we will converge to gradient to local minimum faster. But if we're taking our eta too big, in this example it's bigger than 1, then with each step point is oscillating between minimum, and what actually happens is that we can for example, I won't draw a 3D graph, I just do a 2D graph with x. So actually what happens is, because our graph is symmetrical, so what happens is our point begins to, if our eta is enough small, then it goes just small steps. But if eta is too big, then it begins to oscillate like that. Yes, it can go to minimum, but if eta is bigger than some critical value, which is equal to 0, which is equal to 1, in that example it goes like that. So because our ball is infinitely, which means that if we take and we have 50 steps, our point exponentially grows its distance between point and the local minimum. And if you take like an eta is equal to 2, then the numbers will get astronomically big, like 1 and 14 zeros. So you have to be very considerable with what you choose, because such small difference in 100 and like 102 is enough to increase whole oscillating in like 2 or 3 times. And now it's actually worked for some values of eta, but what will happen if we have several minimums, because in that case we had only one minimum and it was pretty obvious that it's in the center. But what will happen if we actually have something like that? What will happen with gradient descent if we actually... What will happen if this minimum is obviously deeper, but we take our point here, because it just randomly got here? What will happen? Will it find the global minimum or not? So I just edited previous function, editing some sign, which is good for optimizing some rough and not smooth data. And now we've calculated derivatives. You can do it at home yourself, and we've got a plot. So here we have a minimum, here we have a minimum, and these are minimums too, actually, but they're local ones. And it's obvious, you can tell from the color, that they are not the deepest one, and there are only two global minimums. They are symmetrical, and that's why we have two global minimums. So we again do the same, and we've taken our point quite far from global minimums, and we are going to understand if it can actually go to global minimum or not. So again, too small eta, and it takes too much computational effort to do something. So it will just, probably if we even do some more steps, like increase their number in 100 times, then it's actually most probably will stay there, because it doesn't have velocity to get out of this. It doesn't have a velocity like in that example. In that example, actually, we can say that there are, if eta is bigger than eta maximum, then point travel will always get out of this minimum. And it can be said that if we have two shallow minimums, for example, shallow minimum and a deep one, then we can say that n critical here, maximum 1, maximum 2. We can say that this eta is critical, so it means that actually we can consider some values of eta where it can go out of this shallow minimum, but it cannot get out of this global minimum, which means that we have to consider that our problem and task of choosing the best step size, which is called eta, is even increasing it in its complexity. We will just have to tune our numbers to get to the global minimum. And let's say if we can actually do it. So here we can say that we've increased a bit eta, but we've still got stuck in this local minimum. And you can see an interesting result, that we have a bit of zigzagging, a bit of oscillations around here. What will happen if we increase? Suddenly, if we've increased our eta, it's actually got enough speed to get out of this too shallow local minimum, and it got to the second one. So it's again not global minimum, but it's pretty close. And finally, if we are increasing even more, it begins to oscillate pretty chaotically, and for some values it's actually got to global minimum, but I don't think that it will happen in any points, or which means that if we drop it in different points of a graph, we drop here, 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 that it will go actually always to these global minimums. I think that it's just a coincidence, and if we're increasing even more, it begins to oscillate between these global minimums, but further increasing leads to, if we increase even more, then again our point traveler will have enough velocity to get out of any local minimums, and that means that if you increase even a little step size eta, then numbers at which points it travels gets astronomically high, and I just didn't want to bother with tuning some number eta when it's all right, and I can show you this effect, because if I changed it even in like 1 in a 10,000 part, then it's already, as numbers are getting pretty big, and that's why I choose to show you this astronomical exponential growth around of oscillation only in the first example here. And you can actually check it at home when you can just raise this number eta a bit, and you can see what's happening. And so we have two different behaviors that are actually quite interesting. The first one is called zigzagging. If our function has some minimum, and its minimum is quite shallow, as you could see on the graph, then it just starts to zigzag like that, and it doesn't really walk anyway, and sometimes this zigzagging can be even perpendicular to direction of the best descent, and it happens when step size it's not very small, but at the same time it's not very big to get out of this minimum, and a point just tries to get out of this minimum, but it can't, and it just zigzags, and sometimes it can go back. And the second behavior is that it's not always getting to global minimums, and you need points needs probably a lock and a lot of tuning of parameter of step size eta, and it's understandable because gradient descent, it doesn't let a point explore a state like a simulated annealing. It only gets information from the surroundings, and that's why it just from its name one gets always to global minimums. And that's something similar with greedy algorithm, where in discrete systems greedy algorithm can get to some suboptimal states, but it won't find the best solution in most cases, just like gradient descent. And we are going to use it quite often, and in fact we will have another lesson on gradient descent, which will be like probably 1 or 2 lessons, which will be explaining more tuning and improvements in gradient descent, because this gradient descent is the most basic one. It's called vanilla gradient descent, and I have written in useful links an overview of different gradient descents which perform a little bit better than this one. But still, they're just relying on the luck to get to global minimums, but they're pretty reliable when you want to get to local minimums. And your homework includes also writing this algorithm in your optimum lib. You can remember that in the last lesson we've talked about modules, and you still need to keep up with these 2 modules, we've created on the last lesson. And you also need to check what we've done with linear regression using gradient descent. You'll need to find such values of a and b, as you can remember, which are the best fit for the line. And I think that's it for this lesson.